Welcome to radio frequency and millimeter wave IC design class. And in today's class, we'll continue our discussion on non-linearity. Uh, so, I hope all of you know how to characterize a system, especially a third order nonlinear system, and we know how to look at the various components coming at the output. Right. So today we'll continue the discussion on non-linearity, and we will as I mentioned here, we'll talk something about gain compression, or we'll try to understand one of the important performance metric of nonlinearity, or it is a measure of linearity of any system. We call it as 1 dB compression point, and that is based on the circuit's response, something called as gain compression. Let us see what it is. So to begin with, again, I am considering a nonlinear system. Yeah, so today what we will be discussing is something based on the nonlinear effect of a system. We call it as gain compression. All right, so yeah, this is a nonlinear system where this is the input to the system, and this is the output y of t, the response. The system is assumed as non-linear. I hope I'm audible. If there is any issue with the audio or the screen visibility, please do let me know through a message in the chat box. I hope I'm audible. Can you respond in the chat box? Okay, thank you. Yeah, so this is a nonlinear system, and I am considering an input to this nonlinear system x of t as a cos omega t, which is the input to this nonlinear system. Now, based on yesterday's class, we know that there will be a lot of harmonics coming at the output, and even if I consider all such components at the output, if you want to specifically look at the gain of circuit, or if we okay, I'll write the output based on the discussion, the previous class discussion. It is alpha naught plus alpha uh, yeah, alpha 2a square by 2, which is the other DC offset term coming in, plus alpha 1a, which is the fundamental, plus 3 by 4 alpha 3a cube into cos omega t plus etc. So what I have written is this is the DC offset term. Most of the time we will just neglect these terms, hoping that it will actually give a DC shift. We will not discuss about the effects of this DC offset for now. Now the focus is on this fundamental term, because this is the fundamental frequency omega, and the component or the coefficient of this fundamental term is alpha 1 a plus 3 by 4 alpha 3 a cube, right? Now if you look at the small signal gain of the circuits, or usually when we talk about analog circuits, when we talk about small signal gain, the small signal gain is usually obtained by assuming all the higher order terms, especially like harmonics, all those things are negligible. The reason for being those terms negligible is very simple. You can see here, if your a is small, if a is small, I can say that the terms like a square, a cube, etc. can be neglected. It is obvious because when we talk about small a, it can be in milli or microvolt. So the square or cubic terms will be very small, still smaller than that. So if a is small, these terms can be neglected. In such a case, I can approximate the output of this, leaving the offset and leaving all the other terms because of the small value of a. I can write here y of t as alpha 1a into cos omega t, right? Here I can say this alpha 1 is the alpha 1 term here is the fundamental gain, or I can call this as the small signal gain of the system, or the circuit, small signal gain of the circuit, right? Now if I try to plot this, I know that the response should be linear, because the relation between input and output is through the constant term alpha. So if I draw here it as y of t and x of t here, it will be a straight line depending on the value of alpha. The slope of this is becoming your alpha. Delta y by delta x is your alpha in this case, alpha 1 in this case, right? And this response is very clear. This is actually a linear response. And this is true when you neglect all the higher order terms and when we consider only the small signal gain of the circuit, right? But now, now what happens if now initially I considered the case when A is small. Now, what happens if A is becoming larger? What happens if A is becoming larger? What happens to gain? So if A is becoming larger, the obvious the result will be uh, gain will vary. Why gain will vary? Because you can see that I'll write this again here. Y of t is equal to, I'm taking out only that term which is related to the fundamental gain, 3 by 4 alpha 3 a cube into 3 by 4 alpha 3 a cube into, okay, or I can write in this form, a square into a cos omega t, because my input is a cos omega t. Then the coefficients will be alpha 1 plus 3 by 4 alpha 3 a square, right? Now when a, okay, so as I mentioned, now when a is becoming larger, definitely your gain is going to vary, because this is your input signal. Your input signal is here, this is input. Now, when your A is becoming larger, this term will definitely change. This term will increase or decrease. That depends on. Okay, can you respond? Can you guys respond in the chat box? Now, what happens if your gain, if your input amplitude A is increasing? We know that definitely gain will change. Now, what will be the expected change in gain, or that depends on what? Whether my question is clear? Exponential increase. How can you say that it is exponential increase, Lilith? You, how do you assume that you will always get an exponential increase? It depends on what? A is increasing is clear. Now it depends on any other term here. The power of A, yes, absolutely, the power of A. Now, if you look at this term, it is, I'm just looking at these two terms, alpha 1 A plus 3 by 4 alpha 3 A cube. Now, A is increasing. Now, the response depends on what? Anyone else, any other answers? So, A is becoming larger, your gain will vary. Very good, Mino. Yes, it depends on the terms alpha 1 and alpha 3, or I would say it depends on the term alpha 3 here, right? So, yes, I'm getting answers, Shreyas. Yes, thank you. If A is becoming larger, your gain will vary, and that variation is primarily depending on this term alpha 3. So why am I saying this here is, if your alpha 3 term, if it is a positive value, as Lalit mentioned, you will definitely see an exponential increase, or something, some kind of an expansive behavior. So if alpha 3 is a positive term, okay, so now you'll be wondering why, or all of a sudden, why am I talking about this? So for the time being, alpha 3 or all these coefficients are nonlinear coefficients. We know the coefficients of nonlinear terms, and there can be possibility that alpha 3 can be positive or negative. So we are slightly doing a small discussion on that here. Now, we can definitely say that if alpha 3 term is positive, your response will be of one type, and your alpha 3 term, if it is negative, your response will be of a different type. All right. I hope you will agree to this. Now, let us see what happens if your alpha 3 term is positive and what happens if your alpha 3 term is negative. All right. So, for that, what I'm doing here is, I am just looking at the response. I'm just trying to draw the response here for both alpha 3 positive and negative. This is y of t and this is x of t, where your input is a cos omega t and your a is increasing and you are considering the nonlinear terms as well. Now this is again the same situation. Here it is y of t, this is also x of t where a cos omega t is your input. Now I am considering two things. One I am drawing here, if your alpha 3 is a positive term, and here I look at if I have an alpha 3 a negative term, right. Now you can clearly see that your x-axis term here is a. X-axis is your input signal. Now when your input signal is very small, as per the equation or as per the discussion before, if your input signal is very small, you can definitely this term or this term 3 by 4 alpha 3 a cube term can be neglected, and in that case I can say your gain will be proportional to alpha 1, or I can say when your a is very small, the term dominating will be alpha 1a. The alpha 1a term will be dominating, or even I can neglect the higher order terms, so that you will actually get a linear response. But what happens when your a increases? If your a increases, and at that time if you have a positive alpha 3 term, you are expecting an output y of t which is equal to alpha 1a plus 3 by 4 alpha 3 a cube, or to write in this fashion 3 by 4 alpha 3 a square into a cos omega t, right. Now okay, I'll write it in terms of this cubic term only. Now if your a increases, what happens? If your alpha 3 is positive, instead of alpha 1 a term being dominative, I can clearly see another term becoming dominant there, which is your alpha 3 a cube term. So this will become a dominating term there when your alpha 3 is positive, or when your amplitude, input amplitude A increases, right. So this so if you look at this response, we can see that your as your input increases, your output is actually expanding, your output is actually increasing like anything, and this kind of behavior we call it as expansive characteristics, expansive cara. All right. At the same time, if you look at alpha 3 negative term, initially when your alpha 3 is, when your input amplitude is small, there also I can expect an alpha 1a term which is dominating. This is alpha 1a here. But as your input amplitude increases, the dominating term is your alpha 3 a cube. As your alpha 3 is negative, what I can expect is a response something like this, right, where your alpha 3 a cube term is dominating, and since your alpha 3 is negative, you are actually getting a decreasing behavior, or this kind of cara we call it as compressive characteristics. I hope this is clear. If you have doubts, please ping in the chat box. So I am looking at the fundamental gain. So to just to summarize here, I'm looking at a nonlinear system, looking only at the gain of the fundamental term. So if your input amplitude is very small, your fundamental term will have a coefficient of fundamental gain which is alpha 1 into a, and that is actually giving you a linear response, what you can see in the graph here. But now if your a increases, your the gain also will change, gain will vary, and that variation in gain is depending on the term alpha 3 here. Alpha 3 can be positive or negative. So if it is positive, it will show expansive characteristics, and if it is negative, it will show a compressive characteristics. Yeah, that is also right, Kashish. Yes, you are true. Yeah, just to show the effect of this nonlinearity, I have just taken a cube term. That is true. You can even think of looking at the second order quadratic term. That is very true. Yeah. Still, even then, I hope you will agree that it will actually you will get a a kind of this. The difference will be your slope will not be in terms of cube, it will be in terms of square. That is true. I agree. I agree that, Kashish. Yes. Yeah. So yeah, I think what Kashish was pointing out is, since I have taken this x-axis as a cos omega t, the term should plotted here should be in terms of square. That is right. Yeah. Just to show the extension of that compression or expansion, I just have taken this a3 a cube term, cubic term. Right. I agree to that point, and that is correct also, Kashish. All right. So again, to summarize this, what I am telling here, yeah. So, but one thing what we can observe in most of the RF circuits is, um, most of the RF circuits will show, or generally RF circuits will show a kind of compressive nature, compressive characteristics. So I'll just make that point here. Most of the RF circuits show a compressive behavior. The meaning is, uh, alpha 3 will have a negative, or the alpha 3 term is a negative term in most of the real circuit, right? So generally whenever we see the response of any RF circuit, you can see that it will show a kind of compressive nature, and you will also agree to that, at least to this point. Say I am just bringing out the all the characteristics together here. This is input x of t and this is y of t. And in general, what we expect is a cara which is linear. When your input amplitude is very, very small, what I expect is a linear cara, right? So here I'll write this as alpha 1. This is a fundamental term, alpha 1 a, sorry, alpha 1, yeah. Now, as per our previous discussion, if your alpha 3 term is, so this is general, when you neglect all the other higher order terms, this is what you expect. This is what I have drawn here in the beginning, right? Now, there are two cases here. One is you can definitely expect an expansive cara. That means if your alpha 3 term is positive, what I'm drawing is little, yeah. If your alpha 3 term is positive, you can expect a term of kind of this thing, alpha 3 positive, you will get an expansion. Now, if your alpha 3 is negative, this is your alpha 3, if it is negative, you will get a compression. Now, even when we say that, or even if we claim that there will be an expansive characteristics or expansion nature, what we can definitely say is, whatever expansion nature the circuit will have, ultimately this also will have to compress. Why it have to compress is because there will be definitely power supply limits for any circuits, right? So ultimately any circuit should or will have to follow a compressive nature, because we are not working with indefinite, or we are not working with infinite power supply. We are working with a finite regulated small power supply. So even then, if a circuit show an expansive nature, it has to compress ultimately, right? So what you can see on this graph together is, neglecting all the higher order harmonics, you have a linear graph, but with your alpha 3 term, positive and negative, you can see an expansion or a compression. And ultimately, for any circuit, it has to compress because of the power supply limits, right? Now, from the graph, you can see that any circuit, so I'm just stating this, I'm just making a statement that any RF circuit should or will show ultimately a compressive nature. Now, if it is showing a compressive nature, the meaning is, initially we were assuming that the system is linear, and now when we are discussing about non-linearity, this compression is definitely compression is definitely a sign of non-linearity. Now we have to measure this non-linearity, or we have to understand this compressive nature, and we call this as something called as gain compression, right? As your A increases, RF circuits show a behavior something called as gain compression, and that is definitely a nonlinear effect, and this nonlinearity should be characterized. And what we will do next is to understand how we can characterize this nonlinearity by bringing out a performance metric, right? So gain compression is what we ultimately see, and we need a performance metric for this performance metric, and that is called as 1 dB compression point, and we'll talk about this 1 dB compression point soon. So any questions on this? If you have questions, please you can put in the chat box. So we have observed a nonlinearity. Now what we know is generally, or we work with generally linear systems. Now since we have seen a nonlinearity, we are trying to come up with a performance metric to measure the nonlinearity, or to say that, okay, now if this is the case, your system is linear this much. Now if this is the case, your system is linear only this much. So just to classify or to categorize how much your system is linear or non-linear, we are now talking about. We'll now look at on a performance metric, and that is named as 1 dB compression point. I hope okay, so I'll wait for your questions after discussing about this 1 dB compression point. So let's see, or let's discuss about this performance metric. Performance metric to characterize this 1 dB compression point, sorry, gain compression behavior. Now this is your input and this is your output, and in general what I expect is a linear graph. Here what I can expect is this is alpha 1 a cos omega t when you are providing an input a cos omega t as the input. Now I'm just drawing only the compression, because ultimately, or we are just characterizing only gain compression here, right? So this term can be, this can be written as alpha 1 plus 3 by 4 alpha 3 a square into a cos omega t, right? This is the nonlinear term. Now the performance metric is called as 1 dB compression point, and I'll define this 1 dB compression point here. 1 dB compression point. So 1 dB compression point is basically it is the input signal level that causes uh, output of any system or gain of any system to drop by a measure of 1 dB. All right. The meaning is this is your this is your linear system. This straight line. This is your linear system. So from this linear graph, if your output is dropping by 1 dB, so the meaning is, see, at this specific input, the expected output is this value. Now if that value is dropped by 1 dB in the real cara, we define this input as 1 dB compression point, and we mark it as a1 dB. I hope this is clear. The input signal level that causes output or gain to drop by 1 dB is called as 1 dB compression point, and I'm elaborating like this. So say at this input level, so I just put a question mark here, at this input level the expected output from a linear system is this, but now because of the compressive nature, that output is dropped by 1 dB. So So if that is happening at a specific input level, we call this input level as 1 dB compression point, right? So you'll be wondering how this will give a measure. Let me ask this question. Say for example, if your 1 dB compression point is more, what information can you get about the system? If your 1 dB compression point is high value, can you say that your system is more linear, or can you say that the system is more non-linear, or what measure or what understanding will you get out of that? Can I get your response in the chat box? Yeah, the system is more non-linear. So if you have more linear, right? Okay, all right. So if a 1 dB is more, what I can say is system is more linear. Why do I say my system is more linear? Say for example, for a specific system, this is your 1 dB compression point. That means your gain is the input signal level that causes your output to drop by 1 dB is happening only here, right? Now for some other system, if this 1 dB compression point is somewhere here, what can I say about that system? That means your 1 dB compression point is less. Then the system is
More non-linear.
more. Yeah, the system is more. So as your 1 dB compression point is more, your system is more linear, right? If you have a larger 1 dB compression point, so that is where this can be mentioned by considering or comparing two systems. Whether my question is clear? Yeah, alpha 3 more negative, I understand. See, there are two systems. One is having a 1 dB compression point here. This is the 1 dB compression point of system number 1. And this is the 1 dB compression point of system number 2. So which system is more linear, whether the system number 1 or it is system number 2?
System
Which
2.
is system 2 is more linear, right? So if you have a 1 dB, if you have a larger 1 dB compression point, the point is your system is more linear. I hope it is clear now. Yes, Bhavana, you're right. All right. So when you measure, when you write this one, yes, Rahul, I can explain this again. All right. So the first thing to understand here is you should understand what is a 1 dB compression point. So in order to measure the non-linearity of any system, as we have observed that system generally show a compressive nature, a performance metric is evaluated or performance metric has brought out, and that is mentioned in terms of your input, because all these things depends on your input, right? Because if you are increasing, if you're increasing your input amplitude, then only we are actually seeing all these kind of responses. Now this compression 1 dB compression point is actually measured at the input side. How it is measured? You can see that I am actually considering this point. So at this point, the actual linear system should actually provide this much output. You can see that, right? Now, because of a non-linearity at this input, your system response is only this much. That means you can definitely see a so whenever you are seeing this kind, so I'm taking this measure as, or this as 1 dB. Now, whenever you see a 1 dB fall or 1 dB drop in your output at a specific input level, that point is called as 1 dB compression point, right? Now, if you, by looking at the 1 dB compression point or the value of 1 dB compression point, definitely I can say, say if you have a 1 dB compression point here, I can say your system is becoming more non-linear early, or the non-linearity of the system is more. Now, if your 1 dB compression point is happening only here, I can say that from this point till this input, your system is safe. You can apply any input there and you can get a almost a linear response because there is no fall in gain or output more than 1 dB within that point. Okay, thank you, Rahul. All right, so that is about 1 dB compression point. So as I mentioned, this is a performance metric. We should also have a mathematical expression for this. So we will make an attempt to even get that mathematical expression now. So it is very simple to obtain this mathematical expression. Uh, so this point, this is your nonlinear graph, and that point can be defined as, say, 20 log of alpha 1a plus 3 by 4 alpha 3 a cube. This is your this is this point. I hope you will understand, you will agree that this point is equal to this value. Now the value, the actual numerical value, depending on the value of a and the other coefficients, right? Because this is a compressive behavior what I have taken, where your alpha 3 is negative for sure. Now, when this is equal to, when this point is equal to the normal graph minus 1 dB, then your A becomes A1 dB, right? When this value equal to the linear value minus 1 dB, that A is equal to A1 dB. How will I write then? I'll write it as 20 log alpha 1A minus 1 dB. 20 log alpha 1A minus 1 dB. All right, so I hope you guys understood what I have written now. So when this happens, or when this is equal, I will modify this as this A as A1 dB. This A is equal to A1 dB. Now how will I further simplify this? What I need is, I need an expression for A1 dB, or that amplitude. If I still yeah, we can simplify this basically by writing it as alpha 1 A1 dB plus 3 by 4 alpha 3 A1 dB cube equal to 20 log alpha 1 A1 dB minus this also I'll write in terms of 20 log. So 20 log of almost 1.1222 is your 1 dB. So I'll write in this form, and from this I'll simplify, and if you simplify you will definitely get a value equal to A1 dB as, can express in two forms. One is 0.38 into under root of alpha 1 by alpha 3, and just putting the mod value because alpha 3 the compressive nature, it is negative. So or this can be this can further written as 0.145 into alpha 1 by alpha 3 by just by placing 0.38 under root. So this is your 1 dB compression point mathematical expression. So this is useful in solving numericals, or to understand the nonlinearity of a system. Now, the value of 1 dB compression point is depending, or basically that depends on the values of alpha 1 and alpha 3. All right. So if you solve, you will get this. You can give a try. I did not write the intermediate steps here. One more point to discuss. Now, A1 dB, or this 1 dB compression point, what I have mentioned now is expressed in, it is in terms of amplitude. The same thing also can be, also will be expressed in terms of power. Then we call this as P1 dB. So this is the 1 dB compression point when it is expressed in dBm. 1 dB compression point, and it is expressed in dBm. All right. Yeah. So this is about this performance metric, 1 dB compression point, and this is how we understand gain compression in any system. If you have questions, you can just ping in the chat box. Okay, so I will show the simulation of this 1 dB compression point probably next class. So before that, I just want to discuss one more effect of nonlinearity, and after that I can take questions from you guys. So what we have discussed now is called as gain compression. We understood what is gain compression. I hope you guys understood what is gain compression, the two types of behavior, and how we are limiting only to gain compression, and finally a performance metric for this gain compression. Right. So quickly I want to discuss one more non-linearity, and that I want to number, I would like to number it as third nonlinear effect. We call it as desensitization. If you have questions, please hold on. I'll definitely answer those questions soon after discussing this effect. Now, so till now we were talking only about the input signal. So if there is an input signal, there are a lot of harmonics coming in. So we characterize. So we saw the harmonics. We spoke about harmonic distortion. Now we spoke about gain compression. In all these cases, we consider only the input signal, the desired input signal, right? But now we are a little elaborating on that. Assume that you have a receiver. This is the front end of your receiver. This is the antenna, and say this is the x of t and this is y of t. Again, at the front end you assume that there is an amplifier. So I am just characterizing it as a nonlinear system. All right. So as I mentioned till now, we spoke only about the desired signal at the input, but we know that for an RF receiver, at the input side you will have a whole bunch of signals. It is not the single desired signal appearing at the antenna, because antenna is through antenna the system is expected to process only the desired signal, but along with the desired signal you can find n number of signals, because you know this our spectrum itself is overcrowded with lot many signals sending coming in, interferences, and lot many other things. So we are just trying to understand what will happen if we consider, say, omega 1 is a frequency where I have my desired signal or the signal to be processed by the system. I hope you guys are with me. Can I get some response? Yes or no? All right, okay. So this is your desired signal at omega 1. Say it is having an amplitude of A, and say for example this signal is sent or transmitted by a transmitter, but the signal when it reaches the receiver, this has become a very weak signal. Possibilities are there, right? This, I am assuming that this is a weak signal. The reason can be the transmitter was quite far, or due to some other reason the signal amplitude is very small, or signal itself is a weak signal. But some other transmitter which was emitting signal very close to this is having or is emitting a very strong signal here, and I am just marking that strong signal as here, and that can be, say it is at another frequency called omega 2. All right. Now, compared to the signal, or compared to the desired signal, this is having an amplitude called A2. Say, let me call this as A1. And by looking at the signal, I can say that this is a very strong signal. Right. So what I want to say here is, we are considering a strong interferer. If it is accompanying a weak signal at the input of a receiver, what will happen? So this strong signal is not the desired signal, so I am calling this as an interferer. This is an interferer, and this weak signal is your desired one. This weak signal desired one. All right. Okay. Now If I write the total signal at the input x of t, I can write it as a1 cos omega 1t plus a2 cos omega 2t, where a1 is the input amplitude, omega 1 is the frequency which is weak, a2 is the interferer amplitude, and omega 2 is the frequency which it is appearing, right? Now, since it is a nonlinear system and since we have characterized it before, I am writing it as alpha 1 looking only at the fundamental component because we are interested or we want to know what will happen to your desired signal. So, desired signal should have an appropriate gain. If the system is linear, it will only have a linear gain of alpha 1a, but if your system is non-linear, it will definitely have other components. So, I will write this as 3 by 4 alpha 3 a1 square plus I am writing the another component here because now we have two signals. So, 3 by 4 alpha 3 a2 square, and now this I will write as a1 cos omega 1. If you have doubt in whatever I have written now, please refer back to our second class. There we have written all the components by considering two signals at the input, but there we considered both signals of equal amplitude. But now the same scenario, but there are two different amplitudes coming in, right? Now, looking at this term or looking at the the input amplitudes A1 and A2, I can clearly mention A1 is very, very small compared to A2, or that is a scenario what I am considering. In that case, if A1 is very, very small, definitely A1 cube term I will neglect, or I can definitely neglect this A1 cube term. This very, very smaller, and that in that case I can neglect that term. So why I'm neglecting is basically to simplify this and understand it further. So in that case I can rewrite this output expression y of t as approximately equal to alpha 1 plus, since a1 cube term is neglected, now this is only having the second term which is 3 by 4 alpha 3 a2 square into a1 cos omega 1t. I hope you guys understood what I have written here. Since a1 is very, very small compared to a2, this term which can give an a1 cube amplitude is neglected, and the remaining term I have written. Now again, limiting this only to the gain compression, I can say that alpha 3 I am considering only negative because that is the scenario in most of the circuits. I am looking only at the gain compression behavior, or assuming that the system will show a compressive nature. I can further write this y of t as alpha 1 minus 3 by 4 alpha 3 a2 square into a1 cos omega 1t, right? Now look at this. Now you have an output expression which is equal to alpha 1 minus 3 by 4 alpha 3 a2 square into a1 cos omega 1t. I hope you guys are with me. Please respond here in the chat box if you are listening to me. Now, if you look at this, so this is your input signal. This is your input signal a1 cos omega 1t, and this is the term which is giving you a gain, right? Or this is your gain term. And I can say that by looking at this expression or looking at this coefficient, I can say that gain is basically gain is decreasing function here. Already I have taken the negative term alpha, negative alpha 3 as negative. Now I can say gain is a decreasing function of the amplitude A2, because it is alpha 1 minus 3 by 4 alpha 3 a2 square. Now a2 is strong, a2 is large, and a2 is square now. So gain can be observed or gain can be understood as a very decreasing function of a2, right? That means at large values of a2, at large values of a2, this overall term can become large, or it can be even equal to alpha 1. And if that happens at large values of a2, there is possibilities that your gain, the gain to your fundamental term, or gain to your weak desired signal, can be equal to even 0. Now, if the gain to this weak desired signal is becoming 0, what is basically happening? Basically, a strong interferer which is accompanying your weak desired signal is desensitizing the circuit, or the presence of the strong interferer is making your circuit insensitive to your desired signal, or I will say that this phenomenon as desensitization. And in such cases, we call this interferer as blocking signal or blocker, or this is called as blocker. This interferer is called as blocker. So this is also one of the nonlinear effects. So what is happening here? If there is a strong interferer accompanying a weak desired signal, there are possibilities or there are chances that at some specific amplitude or the interferer can make your circuit desensitized, or the interferer can make your circuit not respond to your weak desired signal or give a zero gain to your weak desired signal. So this phenomenon is called as desensitization, and then we call this interferer or as blocker or blocking signal. So we'll better understand this blocking or desensitization further with some numerical examples, and in your next class we'll definitely see the simulation of even gain compression. Right. So with this, I'm winding up today's class, and if you have questions, you can ask. Thank you.